Good morning, Dr. Nguyen, Dr. Pauls, ladies and gentlemen. I appreciate this opportunity to present my project evaluating the efficacy of FTIR techniques for organic characterization. My name is Daniel Moseley, and I'm an advanced technician in the Organic Deposit Analysis Lab at SUEZ Water Technologies and Solutions in Tomball, Texas. Now, the role of SUEZ Lab in Tomball is to provide both analysis and solutions for difficult problems that arise in water treatment and industrial process activities. Now, these include, though they're not limited to, fouling of streamlines, corrosion events, and filter failures. My particular role is one of an analyst, providing characterization data for the organic components of samples brought to us by these fouling events. And while my focus is on the organic components, my analyses are not limited to the organic constituents, and in fact, inorganic components can interfere with or influence our organic characterization. Now, in the Organic Deposit Lab, the primary challenge for us is characterizing deposit samples that are insoluble in organic solvents. Our primary means of characterizing functionality of compounds is by FTIR. But this can become difficult to accomplish using traditional transmission sampling techniques with the samples we use. Now, in particular, utilizing KBR pellets can be very difficult, and it's prone to error as well as being more difficult to replicate the results. As a result, by the time I came into the lab, it had nearly completely transitioned to attenuated total reflectance, or ATR, in order to make sampling easier. Now, the primary question for me became whether we sacrificed critical aspects of characterization of functionality by switching to ATR, and whether or not ATR was sufficient for our characterization purposes. Now, to set up the sample situation, I'm going to briefly go over the fundamental considerations of FTIR theory for both transmission and ATR techniques. Now, infrared or IR radiation is already a low energy radiation, and it's responsible for many of the molecular vibration modes that we see. The absorption of energy by matter causes the excitation of vibrational motions in molecules, such as stretching, bending, rocking, etc., and each of these vibrational modes is wavelength dependent. Now, as is typical in spectroscopy, the relationship between wavelength and energy is integral. In FTIR, the key factor is the reciprocal relationship between energy and wavelength, which translates to a direct relationship between the wave number, which is the IR spectral function on the x-axis, and energy. Now, what this means practically is that the bands of high wave numbers on the spectrum have higher energy, while lower wave numbers correspond to lower energy. Band location in the spectra, then, is dependent on the bond force strength and the mass of the atoms involved. And Hooke's law here describes the force proportionality of springs, but it also applies to molecular bonds. So imagine a bond in its relaxed state that then stretches out as far as the mass of the greater atom pulls on the smaller one. Now, in order to recompress that bond, energy is required. And so the greater the mass of the atom that is attached and pulling on the bond, the greater the energy required to reposition it into its compressed state. Now, for ATR, an additional aspect is observed. In transmission mode, the IR radiation would pass straight through the specimen and be attenuated by the specimen absorptivity. But in ATR, the IR radiation is reflected by a series of mirrors towards the internal reflective element, or the IRE, which in this case is a diamond window. Now, once it reaches the IRE, some of it is reflected away and some of it is refracted out past the IRE, and some into it. Now, at some point, the angle of incidence that the radiation hits the IRE is at such an angle that the angle of refraction becomes 90 degrees. Now, when this happens, the radiation can no longer exit the IRE, and total internal reflectance is achieved. Now, this is the point at which the angle of incidence is now the critical angle. But now the incoming and outgoing beams are taking up the same space and undergo constructive interference, causing the amplitude of the IR beam to be greater on either side of the boundary of the IRE and the specimen. Now, since it's already at the surface, it doesn't have anywhere left to go except up, and it impinges on the specimen in an evanescent wave. Now, the evanescent wave penetrates the sample at a depth determined by the wavelength that the specimen absorbs, and the refractive indices of the IRE in the specimen. So in order to have a penetrating evanescent wave, the refractive index of the IRE has to be greater than the specimen's refractive index. And so I want you to note especially how the depth of penetration in the depth of penetration formula here in the left corner is directly related to the wavelength. Now, the trouble we run into in ATR is that the depth of penetration is greater in the fingerprint region, that is, from the region from approximately 1500 to about 400 reciprocal centimeters, or wave numbers. It's greater in the fingerprint region than in the higher wave number, lower wavelength region. The lower the wavelength, the smaller the penetration, as can be seen in this spectrum of 2-propanol in figure A. The raw ATR spectrum in blue indicates a much lower intensity in the higher wave number, or lower wavelength region. Now, what's important to note is that the peak ratios can be affected as well, and that can have disastrous effects on characterization. Most IR software has a relative intensity correction factor that adjusts the intensity of bands by multiplying the original intensity by a correction factor. Now, from the equation, you can see that if we were to correct the spectrum from 400 to 4,000 reciprocal centimeters, the intensity would be multiplied, the intensity of the original spectrum would be multiplied by a factor of about 0.4 to 4.0 in a linear ramp-up. So the greatest adjustment is going to be in the low wavelength region. And as an aside, just to demonstrate how we sometimes have to improvise, since I did not have an official volatiles cover like Figure B shows and did not have the budget allocation yet to purchase items, I recreated one using items from a hardware store in Figure C, and it accomplished the same goal of limiting evaporation of volatile compounds. Now, what's important to note about the previous slide is that the relative intensity correction only adjusts the intensity of the spectra, but it doesn't take into account the anomalous dispersion effect that differing refractive indices have on IR radiation. So, as can be seen in the spectrum of water, in areas where the sample is highly absorbing, IR radiation is refracted greater, and bands can shift, such as in the OH stretching region and the OH bending region here around 1640 in the water spectrum. Now, most literature is going to consider this to be a minor issue, as the general refractive index of 1.5 is assumed for most organic molecules, and the relative intensity correction is enough to compensate. And this may be potentially true for most organic molecules. The trouble is that most of our samples are not 100% organic, and inorganic components may contribute to a higher refractive index that brings it closer to the Diamond Window's 2.4 refractive index. And this can lead to significant band shifting that interferes with library searches. More recent software additions take into consideration the effect of the sample refractive index and its relationship with the evanescent wave, electric field, and absorption coefficient of the sample to correct for this. The problem is that one has to manually enter the sample and IRE refractive indices to make use of this correction factor. Now, I've been noting that the library searches could be affected by the anomalous dispersion effect, but we have to see this effect in action in order to really appreciate it. So here we have a standard of dimethyl terephthalate. Now, what's noticeable here is that the overall shape is generally consistent across IR techniques, but intensity and band location of higher absorbing bands can see some differences, and this is noticeable even in our previous spectrum. So to make it a little more pertinent, here in the carbonyl region, near 1720 wave numbers, the carbonyl region experiences shifting that can be corrected when taking into account the 1.515 refractive index of dimethyl terephthalate. But what's particularly remarkable in these segments of the spectrum is not only the band shifting in the carbonyl region or in the CO region on the right, but in the CO region on the right, the peak ratio changes between the ATR and the corrected spectrum. As you can see in the ATR raw spectrum in green, compared to the red advanced correction and the original, well, the transmission spectrum in the purple, we can see that not only has the band shifted, but both band ratios have changed as well. Now we can almost immediately see the effects of these band shifts and ratio changes in the library spectrum. The transmission spectrum gives us a close match with a hit quality index, or HQI, of 87 as our start. But both the raw ATR and the relative intensity correction factor spectrums, on the other hand, they may bring it up as the top hit, but the match is lowered to a hit quality index of about 62. Now, meanwhile, the advanced ATR correction factor improves our HQI and brings it up to 85. Now, the challenge, of course, is that this is of a pure standard with no other components, and the refractive index is known. In practice, our samples are often mixtures, and many components, including inorganics, can impact the refractive index. However, if looking at the spectra by eye, it's clear that even with some shifting, the peak ranges are consistent with dimethyl terephthalate, as are the band ranges for previous unknown sample examples. So while library searches may be more difficult under ADR conditions, functional characterization itself may not be improbable manually. Now, we'll see a slightly different story with this spectra of dolomitic limestone. Now, while the advanced ATR correction does improve matches for carbonate components in the dolomitic limestone sample, as we might expect, the relative intensity correction also displays some component matches for dolomitic limestone with carbonates as well, while the ATR raw spectrum does not even register any form of carbonate as a component. So even though it's not as thorough as the advanced correction, the relative intensity correction can at least aid in supplying reasonable component suggestions. Now, with those considerations in mind, we need to see how those factors can affect functionality characterization in practice. The problem, again, is that we're often dealing with insoluble samples that are difficult to get spectra from in the first place. Coupled with the fact that our libraries are all in transmission mode, we need an optimal way to characterize samples in ATR, at the very least to be able to characterize their functionality. Now, libraries are a good first resort for that, but in reality, most of the samples we get from fouling incidents are unlikely to match library reference spectra. Secondary to library matching is to ensure that the ability to visually characterize is not significantly compromised between transmission spectra and ATR. And so sample preparation that we use begins with drying the sample at 65 degrees Celsius and extracting, if we have enough sample to extract, with dichloromethane. Now, to prep for transmission mode, a laborious method of pressing out the KBR pellet is necessary. And it has to be noted that the pellet with the suspended sample is not only necessary, but a blank KBR pellet background is necessary as well, which adds yet another step to the sample prep process. And it's also often good to collect a background of the atmosphere as well, which adds a third step. With ATR, the solid sample needs only be ground and applied with pressure against the IRE. Now, in this sample of a ferrocyanide that we come across, two things become apparent. First, the stronger peaks are clearly shifted when viewing the raw ATR spectra compared to the transmission spectra. And applying the relative intensity correction factor does not adjust, it does adjust the intensity, but it does not significantly correct the wave number shift of the cyanide peak. Now, second, not all of the bands experience significant shifting. If we look over into the fingerprint region, we'll notice that some of them remain in place compared to in the ATR raw and the relative intensity spectrum compared to the ATR advanced correction and the transmission spectrum. Now, this is because theory predicts the significant shifts from the anomalous dispersion would shift only for strongly absorbing peaks. Now, this could work in our favor, as it might help us to get in the ballpark for characterization. And even with the anomalous dispersion effects shifting strongly absorbing peaks, in this case, bands are still within published ranges for identifying compound families. Now, in this particular sample, we can once again see that there are significant shifts by viewing the amide 1 and the amide 2 peaks right around 1630 and 1520 respectively between the ATR and transmission. And this could affect searches. But not only do we see shifting in the peaks, but you may also note that the peak ratios between the amide 1 and amide 2 change from approximately 1.5 to 1 to more of a 1 to 0.8 ratio between the ATR and the transmission spectra. So if we had a corresponding library spectrum from transmission, we might have a difficult time matching it purely by library searching. And to highlight that, this highlights the biggest problem with the advanced ATR correction that makes it rarely useful for our purposes. See, the key factor that makes it work is an a priori knowledge of the sample refractive index. So if I were to just guess at the refractive index, it could affect the band shifting significantly in the wrong direction and negatively affect our ability to correctly identify compounds. Now I realize as I put here refractive indices changes from 1.1 to 1.5 that below 1.3 is probably pretty unrealistic given that the refractive index of water is 1.3 itself. But the point I was making with this was to illustrate that putting the refractive index incorrectly into the advanced ATR correction can significantly shift the band potentially in the wrong direction. Now, band shifting and peak ratio change may be heavily impacted by anomalous dispersion effects, but anomalous dispersion effects are not the exclusive source of band shifting between transmission and ATR spectra. There are other factors in ATR that can shift bands. Now, every formula that we previously considered for ATR, from the depth of penetration formula to the relative intensity correction to the advanced correction, they all assumed that the sample specimen had close contact with the IRE, or the diamond window in our case. Now that may be easy enough to achieve for liquid samples, but for insoluble solids, it requires them to be pressed uniformly against the IRE, often by the use of an anvil putting pressure on the sample against the window. Now there are two things that can affect the uniformity of contact between the sample and the IRE. First, the varying pressure from the anvil may leave some air gaps between the sample and the IRE. Some ATR accessories come with a pressure gauge that would make replicating the amount of pressure achieved a bit easier. However, the second effect can come from non-uniform particle size and shape of the sample. Now, it's typical to grind the sample in a mortar and pestle for a few minutes to achieve a powdered sample, but not all samples are so easily ground, and non-uniformities can directly impact the band shape and thereby allow air gaps, which affect the peak ratio and the wave number. And we can see from these spectra here, in particular with the red spectra, as compared to the green spectrum in figure A, we can see the low pressure in the red spectrum, and we'll notice that there's a band intensity and band ratio change between the red and the green spectrum. So between the low pressure and the high pressure, we notice in these SIO peaks, there's a significant band ratio change. And published papers have shown exactly the same effect as we can see in figure B. Now, meanwhile, resolution is also a potential source of band shifting. If a sample is collected in a lower resolution than the library spectra it's compared against, for example, peaks may merge together and shift, or they may disappear altogether. Now, one may find that by switching to a higher resolution, that what you thought was 2 peaks at a certain wave number are really 3 peaks, or some similar instance. This is particularly notable in our spectra, our yellow spectra, at about 32 reciprocal centimeters resolution compared to the red spectrum at about 2 centimeters resolution, where we can see a difference between not only the band shifting but also the number of peaks in this region. Now, thankfully, IR is not the only technique in use for characterizing samples. As supplemental techniques, we also use SEM and EDS for inorganic components, and an elemental analyzer for CH&S composition. So, is ATR sufficient to characterize our solid samples? Well, the answer in general is yes. Really, in general, the peaks fall into published ranges for specific families and functional groups, and the relative intensity factor still aids in bringing peak intensities into a reasonable state. But there are other aspects that have to be kept in mind. First of all, we don't typically see pure compounds. Usually we have a mixture of organic and inorganic compounds, which could affect band location and peak ratios, and that needs to be kept in mind. Functionality can be derived, but it could be challenging to identify specific compounds without comparing them to custom libraries with spectra obtained under the same conditions as samples are. And that said, for our purposes, ATR is more suitable and advantageous over transmission for our sample volume and as central but not exclusive information for characterization of samples. Now, even though there are challenges with heavy inorganic components, there have been a number of instances where largely organic samples have been accurately identified by ATR by comparing with transmission library spectra using only the relative intensity correction. And while I didn't have time to demonstrate this in my project here, it's also feasible to get a better reliable library searches by doing region searches on the ATR relative intensity correction spectrum and comparing them to transmission reference spectrum in the libraries. For other more difficult to characterize samples, additional information from supplementary techniques. But there are still some areas where our spectra characterization can be improved. Now, at a sample prep level, we're looking into investing in a mechanical grinder and a sieve in order to more uniformly grind our samples into powder and make sure we get a more uniform contact with our IRE compared to just grinding them in a mortar and pestle by hand, which could result in non-uniformities. Now, meanwhile, we're also beginning to generate our own library with products and standards that are of particular interest to our customers and represent more commonly seen components. And a future goal is to be able to get some of our own products and begin to work on quantitation in our extracts. And so our goal is to constantly improve both our turnaround time in the lab and the quality of characterization of samples that we receive, and we anticipate being able to do so with these adjustments using ATR's FTIR. So I thank you for your attention, and I look forward to answering your questions.